Yeah, hi everyone. My name's Jim Vollinger. I'm a teacher at the Northfield Mount Hermon School, boarding school in western Massachusetts, up near the New Hampshire-Vermont border. And I'm here with Joe Molo, a student from Deerfield Academy, who's checking my work as we go around. And today we're going to put cubics in graphing form. I want to give a shout out to my buddy Sam Richardson, who had helped me to start looking at cubics. And together, back in the 90s, we did some work in this area. I want to give him oodles of credit for this video. But I've looked online, and there doesn't look to be too much out there that's extensive. So I'll talk about cubics and graphing form. And we're going to start talking about what graphing forms are, work our way up through the linear, quadratic, and then get to the cubic so that it might have a little bit more of a geometric underpinning. All right, so might be more useful instead of saying mx plus b to start with polynomials written in the ax plus b, ax squared plus bx plus c, and ax cubed plus bx squared plus cx plus d format. And of course, we could continue with quartics and continue on with that. But these seem to be the ones that, and from a high school standpoint, probably we can learn the most from. And so we want to look at exactly what a graphing form is. And I believe that a graphing form will take the number of terms in a polynomial and reduce them, so that you're not considering quite so much from a graphical standpoint. So what do I mean by that? Well, let's look at just ax plus b. So ax plus b, some linear component and some constant component. And it's not too difficult to think about what that graph will look like. So in essence, it is a graphing form. Textbooks say mx plus b. You get a sense of what it looks like immediately. But if we really break it down to its simplistic components, then you really are adding two graphs and picturing what it is. Whereas if you rewrote ax plus b in the a times x plus b over a format, then you really are going from two terms to one, and you have the graph with some pertinent information, that being minus b over a gives you a value of 0, which really breaks your linear function into positive values and negative values. And I think that's useful to talk about from the get-go. So then if you move to the NA, the A term, I believe we can just refer to as a linear converter. What would the A term be in a quadratic? Well, it's a quadratic converter. And in the cubic converter, the quadratic converter would be change in y over change in x squared as measured from the vertex. And the cubic is a little more difficult to understand. It's the change in y minus the linear change in y over the change in x cubed as measured from the point of inflection. I'll be talking about that at the end of this video, probably about 10 or 15 minutes from now. And anything I'm saying too quickly here, with modern technology, all you got to do is play it again. So Joe's going to move the camera now because we're doing this on the fly. Excuse my handwriting, but it is what it is. So let's look at a quadratic, and let's put a quadratic in graphing form. So quadratic, ax squared plus bx plus c, quad being a four-sided figure. So here's an example of a quadratic, x plus 2 times x plus 6. The roots we can see, -2 and -6, because that's what gets rid of the area of this quadratic. But we can't use a square root on that, an inverse operation on that, because it's not a square. So it seems logical to turn it into a square, and so an equal sign we can think of as may be written as. So we can write this calculation in the x plus 4 times x plus 4 minus 4 aspect. And it makes sense because I'm taking the longer side of the rectangle and making the shorter side longer, the longer side shorter, and reconfiguring it, and then just making a quick adjustment. And so what does that create? It creates a I'll just use my hand here, x squared plus, 8x plus 12. A three-term expression is now a 2, which is going to be easier to see from a graphical standpoint, which we'll look at over there in a second. Again, the roots of this were given the way it was originally written, whereas the vertex of this is written. Why is it the vertex? Because the smallest area a square can have is 0. Any other number squared is going to give you a positive result. And so what makes a 0 in this case? -4 gets rid of the dimension, and therefore the area. And so that's going to minimize this calculation. Let's see. So if we wanted to write a quadratic in graphing form, we would reduce the 3 terms to 2. And it turns out that the value of minus b over 2a is the average of the roots. I mean, we know the symmetry of a quadratic. What's between -2 and -6 is -4. We do that in class all the time. So multiplying a times x squared gets me the first term. I need bx, and b over 2a squared times a is going to get me bx. And we can see that in this diagram as well, that the x squared term is going to have a 2-to-1 ratio. And we can perhaps do a quadratic very quickly over here. I'll put it in graphing form. So 4x squared minus 24x plus 7 is a typical problem done at the high school level. And that's 3 terms. It's got a quadratic term. If we graph it, it's got a linear term, decreasing linear term. It's got a constant term. And what we're trying to do here is envision what would happen if we put these 3 graphs together. We'd be adding all 3 y values. And it's a little more difficult than if we write it in graphing form, which I'm going to do for you in a minute in a shortcut fashion, much quicker fashion than completing the square. We can see from this that, well, I guess I've simplified it here, that x minus 3 squared times 4 is just a quadratic centered at 3, 0, and minus 29 is an altitude here, so y equals minus 29. What would you get if you added these 2 terms? Well, you'd just be going the quadratic shape down and making the vertex here. So 2 terms are much easier. 2 graphs are easier to look at than 3 graphs, I guess is my point. And that's what graphing forms are. And turns out that minus b over 2a, the average of the roots, centers this quadratic, which makes perfect sense. If we were to do one quickly, here I'll do that again for you just to show you how you could do this on the fly. So y equals negative 2x. I'll slow it down a little bit, but that gets us our first term. Opposite signs means that you have a negative here. B over 2a, 20 divided by 4 gets you 5. If you put a 0 in here, you get negative 8. If you put a 0 in here right now, you get minus 50. You don't want minus 50, so you can get rid of it. You do want minus 8, and you have the marker, which allows you to do these things pretty quickly. So this is equal to minus 2, x minus 5 squared, plus 42. So that gives us a very quick look at the vertex, 5, 42. And we also knew that 0, negative 8 is the y-intercept. And just to go back to the change in y over the change in x squared, so the change in y from 42 to negative 8 is minus 50, and the change in x squared is 25, and 25 into negative 50 is indeed negative 2. So there's your quadratic converter as measured from the vertex. Now we're going to look at cubics. All right, so here's a cubic. Here's a typical cubic. 2x cubed minus 6x squared plus 5x plus 10. What can we say about that cubic? Well, I'll start from scratch. Reading it backwards often is the best way to look at local behavior. So locally it has a y-intercept of 10. The next term will tell you what it's doing there. It's going up at a 5-to-1 ratio. The size of this term will determine whether or not we have maxes, local maxes and mins. Probably do, but it's got, its next trend, its next trajectory would take on this value, and its end behavior would take on the first term's behavior. So we probably have a cubic that looks like that, but we'll put one of these in graphing form in a moment. But if we think about what's going to reduce this in terms of terms from 4 terms to 3 terms, well, it's geometry again. It's all about the average of the roots. So we made one up here that we've got a box-shaped graph here, which got volume, length times width times height. And that's what's generally done at the high school level, is practicing the factoring of that, so you can see the roots. Well, we can see the roots here: 9, 2, and 4. So 9, 2, and 4, which add up to 15. And if we wanted to reconfigure this so that it's a perfect cube, which, by the way, allows us to use a cube root, and that's one of the benefits of the quadratic, putting it in graphing form, allows you to solve equations because you can use a square root on something that wasn't a square before. So this would be helpful to put some cubics, can be written in perfect cubes, and a constant, but they're a little more complicated, which is why the cubic formula took so many years to have somebody come up and figure out. But back to minus b over 3a, which in this case is 15 divided by 3, which is equal to 5. That's the key number. That's the x value of the point of inflection. It's going to be the x value of the point of inflection for this particular cubic. So we multiplied this out, I guess, on the next board. So we'll go over it, show you the work we did on that, and begin working with this particular cubic. We'll put it in graphing form. So first off, how do you get the first two terms of this? Because we're going to put this in graphing form without the use of calculus. And it turns out that a times x plus b over 3a cubed gets you those first two terms. And we also multiplied out our function here. We took the roots, multiplied it out. And so the volume of that cube was 2x cubed minus 3x squared plus 124x minus 144. So we're going to put that in graphing form in just a moment. But back to what we were talking about here, we actually did the expansion. We did the a times, I wrote 2 here. I'm so used to doing quadratics in my class. So we wanted to cube that. And we did it out. And just to prove that those first two terms were created, it's easy to see the first term, x cubed times a. We did the expansion. It's on tape. You can, or just dated myself. You can watch it on the computer. And we just proved to ourselves that, yes, we've got, probably got Pascal's triangle there or something that could do it as well. But we did it out. We got bx squared, which is what we wanted. So rewriting ax cubed plus bx squared as one term versus two is going to give us the advantage of getting rid of the quadratic. Here's a cubic. Here's a quadratic term. Now we're only getting the cubic term as a graph, which will be shifted off the origin. Okay, so now we're going down, and bear with us as we continue to move around this room. All right, so here's the general graphing form for a cubic, and I'll define the terms in a moment, but if you'll notice, the quadratic term is missing. So what we're going to get here is we're going to get a cubic term. We're going to get a cubic term. We're going to get a linear term, and we're going to get a constant term. And so now we're adding 3 graphs versus the 4. And so it's easier to envision what's happening here because the rate of change of the cubic at the point of inflection is 0. It's not changing. So any change that's going to occur is going to take on the characteristics of the linear function. And so putting in this form will allow us to see what's happening. So we're going to do that with that particular model in a second. But in terms of textbooks, I suppose if you're going to write it in terms of textbooks, h then is defined to be minus b over 3a, the average of the roots, because of the geometry that we're looking at. The average of the roots of a quartic would be minus b over 4a, and that would get rid of the cubic term. So I'm not sure what you can use it for, but that's just going to continue that process through all the higher degree polynomials. And the multiplier here, this linear converter, I'll call it m for obvious reasons, is actually c minus 3ah squared. And the way you get that would be, hopefully you can see that if we multiply this x minus h, we need c. We need that value of 124. So we've got to bring it in. And that expansion, if we continued it, which we didn't because of time and space, we're going to get rid of the linear components of that expansion, which in this case are minus 3ah squared. That gets rid of, that brings in what we need, and then we'll make the final adjustment with the linear aspect by adjusting to what we need. Okay? And so to find this value k, the easiest way to do it would be to plug in minus b over 3 and just do a simple evaluation. And the nice thing about that is we're going to get a 3-to-1 ratio in the quadratic to the cubic term for the geometric reasons similar to what we talked about with the squares. All right, so here was the given quadratic. This is it written in factored form. Those were the dimensions of the box that we had. And you can take the A term, which we'll talk about in detail in a little while. Minus B over 3A is not hard to find. So, the same process for creating it. You take what you want, and you basically write plus B over 3. Well, you look at the signs, they're opposite, so it's a negative in this case. And then you just do B over 3A, the magnitudes. And that's 30 over 6, and there's your 5. So it's not hard to create that number. And then if we put 5 in, you'll see that the first term is 250. And then the second term is minus 750, which is your 3-to-1 ratio and opposites. And so that's a special moment in the volume of that cubic. Probably gets rid of the volume. And have to look at that another time. And then plugging in 5 to 124 gave us 620, and then minus 144. So f of 5, this function evaluated at 5 was negative 24. So that's the y value of the point of inflection. So we now know that 5, negative 24 is the point of inflection, and we know that it's decreasing at a 26-to-1 ratio at that instant. So I don't know if I've actually graphed that yet, but so somewhere over 5 units, down 24 units. Down here, we had roots at 2, we had roots at 4. So we've got this, we've got roots at 9. We could have at least a sense of what the cubic looks like. But from a graphical standpoint, again, we now have 3 terms instead of 4. So what does the graph of 2x minus 5 in parentheses cube look like? Cubic, rate of change at 5, 0. Minus 26, x minus 5, linear component cutting through at 5, 0. Negative 24, a constant of negative 24, which is simply going to move this graph down to this location because both of these are values of 0. And so we get our point of inflection down here. And the interesting thing here from a precalculus standpoint is maxes and mins, because this is when you graph something like this, you're going to get a graph. When you put those two together, you're going to get a graph that looks like that. And so we've got these local maxes and mins. And we'll talk about how you find those in a moment. But when does it occur? When it occurs, the rate of change at these locations is 0, so it's really opposing rates of change. It's going to occur when the cubic is increasing in terms of magnitude, the same as this is decreasing, as the linear function is decreasing. And there's a little formula for that. And it is as follows. H plus or minus the square root of minus m over 3a. We'll find those x values. And I just put the simplest cubic I could think of, the cubic component, the linear component. So this is in graphing form. And our h in this case is the quadratic term is 0. So 0 over 3 times 1 is 0. So that's easiest to look at. And the linear component's minus 12, so the opposite of that is positive 12. And 3 times a is 3. So you've got this quadratic cubic, the x cubed, and the minus 12x producing this cubic. And so the negative 2 would produce the local max, and positive 2 would be the y value, the x value producing the local min, this y value. So it comes from this formula. And so this is a very rich discussion of cubics. We're getting away from looking at roots, and we're really starting to talk more about how these graphs interact. I like to talk about polynomials as numerical tugs of war. It would be nice to maybe look at one of these components where x is 0, and you've got your terms here, and then maybe moving to 0.01 and looking at the change in the table would be useful. I'll do that in class with you. And that way you can get a better sense of why reading polynomials from local to n behavior gives you a sense of what the polynomial looks like. But at the beginning of the video, I did mention that the a term of a cubic really comes from the change in y minus the linear change in y over x cubed. So I thought I'd do that with the y-intercept. This is the point of inflection. This is the y-intercept, 0, negative 1, 4, d4. And so let's talk about our change, our change from negative 24 to 144 is minus 120. The linear component came from plugging in a 0 here, and so that's positive 130. And so we're going to subtract that, which is minus 130, and we're going to divide that by the change in x cubed from point to point, which in this case is minus 125. And so you get a value of 2 for the A term. So that's another aspect of this. And there's more to talk about, but didn't see anything out there on the internet that looked like it really talked about these things at all in depth. And I know I talked very quickly, but as I say, you can always go back and correct me on anything that you think that I've misstated here. Okay, so that's it from Joe and myself, and happy holidays.